All right, so let's get started. So I've split this up. I've split this up based on just the study guide. So I've got the study guide here. It's split into different categories, right? And so that's just how I've split up the review. I tried to get questions on pretty much everything that's on the study guide. We're not going to be able to talk about every conceptual thing, and we're not going to be able to talk about every type of question that they could ask you, obviously, right? The goal of this is for you to recognize things that you once knew or were once supposed to have known, so that you can figure them out on your own. Does that make sense? So we'll go through a lot of problems and we'll talk about a lot of stuff, but don't expect this to be like to cover everything. That's not my responsibility. That's on you. Sound good? Okay. I know I asked sound good a lot. You don't have to respond. You've already learned that. All right. So let's just first define chemistry and matter. This is like a really easy multiple choice question that they could ask you. So what's chemistry? The study of matter. And what's matter? Anything that has mass and takes up space. Okay? Technically, the definition of chemistry is the study of matter, and then it's like its composition, its reactions, its energy changes, stuff like that. I don't know if you remember that from the first day of class, but understanding that it's the study of matter should be fine because it's multiple choice. All right, element or compound. Let's call it out. This guy, that's an element. This one? Compound. This one? Element. Okay, so hopefully you notice a differentiating characteristic there is that an element only has one type of atom. Then it's an element, right? Doesn't matter how much of iodine I have. If it's just iodine, it's just an element, okay? Otherwise, it's a compound. Okay, and then homogeneous or heterogeneous, these are mixtures, right? So milk, yeah, that's homogeneous. This would then be heterogeneous. Ha, 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 okay. Salt water, homogeneous. And chocolate chip cookies? Awesome. Except, do you know how chocolate chip cookies were invented? So this woman who had like a bakery, she always made these chocolate cookies, but she ran out of baker's chocolate, and she's like, well, I have semi-sweet chocolate, so I could just break it up into little pieces, thinking that when I put it in the oven, it's going to melt and make the cookies all chocolate. Guess what didn't happen? That. Therefore, we have chocolate chip cookies. So they were supposed to be homogeneous. That's the moral of the story. Okay. Questions about that? Okay. Okay. Quantitative reasoning, I don't even know what that means other than like simple math stuff, but it was the name of the thing on the study guide. So if tire pressure is measured with four different gauges twice, so 1, 2, okay, and the actual pressure is 20 psi, we want to know if these are accurate or precise, or both, or neither. Okay, so maybe take like 10 seconds. You're allowed to talk. Ready, go. Okay, bring it back. So, what about the first one? What do you think? Accurate. That's accurate. Is that stupid? Yes. Yeah. Yeah, that's dumb because none of those numbers are even close to 20, right? 20 is the real thing. But what makes it accurate? The average is 20, so it's accurate, okay? And then what about these ones? These are precise. Okay, they're nothing close to 20, but they're all close to their average. Okay, they're clustered, yeah. We need to know, like, how to calculate this. I think that if they're going to ask you a question, it's going to be pretty obvious, okay? Just take the average and compare it like we just did. Okay? One thing I don't want to I'm not liable for this, but I'm pretty sure that the actual questions on the final are more straightforward than questions on midterms have been, but people still don't do as well because it's been longer. Does that make sense? We're not asking you about all the little intricacies of stuff. Again, I've actually never seen the final because you guys take it and then I go home. So but I'm pretty sure that's the case because I'm pretty sure that if they gave you questions as nitpicky as they do on midterms, on the final, the grades would be way lower. So I don't know because you guys finish and I go home. So yeah, sorry. At the same time, if you know the average, is it going to change the way you study? Who said yes? It's a lie. Okay. All right, now we're talking about the history of the atom. We are hauling. Look at this. It's because we haven't done anything hard yet. Okay, what did these people discover? Talk to the person next to you. Take 30 seconds. It left you? Oh. Or you left it. I think it's yeah. It's like, did Christ leave you or did you? No, you left. Yeah. Okay, let's bring it back. Bring it back. Okay, so what was Dalton's stuff? Yeah, so he said atoms were like, I know this isn't like a discovery, but he described atoms like billiard balls. So what things made that make sense? Like he didn't just pull it out of nowhere, right? Yeah. Yeah, was he the guy who actually discovered, like did that? Okay, cool. Thanks for the confirmation. I always forget. But yeah, so the law of definite proportions and the law of multiple proportions. And do you want to go over those? Okay, so definite proportions, that says that for any given compound, my ratios of elements is defined. Does that make sense? The proportions are defined. So it doesn't matter if I have a glass of water or a lake of water, there's always 2 grams of hydrogen for every 16 grams of oxygen. Does that make sense? Those proportions are defined, okay? Yeah?
Didn't Dalton propose the multiple proportions one?
Maybe that was it. So let's talk about that now. So multiple proportions says that for different compounds made from the same elements, how do I say this best? Let's say I'm combining nitrogen and oxygen. If I start with 14 grams of nitrogen, I can either react it and combine it with 16, is that right? Yeah, 16 grams of oxygen, or 32 grams of oxygen, or 48 grams of oxygen. Does that make sense? I can only combine it in proportions that are multiples of each other. The multiple proportions. Okay, so because this is before they knew about atoms, it makes sense to think, okay, so if I have this much nitrogen, I can either have 16 grams of oxygen, or 32, or 48. So maybe oxygen is only available in unit packets. Does that make sense? So it would make sense to say, okay, it makes sense to Dalton that these atoms are like little billiard balls, and you can have 1 or 2 or 3, but not half. Does that make sense? A little bit? Okay, what's up? I don't think so. Nope, I don't think so. All right, so he said atoms were like billiard balls. Cool. What about Thomson? Yeah, this was the cathode ray, which means he discovered what? Yeah, he discovered electrons, and somebody I think said it, and he discovered the mass to charge ratio. I don't know that you totally need to worry about that, but from his little experiment, he could figure out the mass to charge ratio of the electrons. But without knowing the mass or the charge, he didn't know the mass or the charge, if that makes sense. He just knew the ratio between them. And so what model of the atom did Thomson come up with? Yeah, the plum pudding model. Because he now realized, okay, these aren't billiard balls, because I know that there's electrons inside. So he knows that there's something smaller than the atom, okay, inside the atom. So he said, all right, I'm going to pretend like I've got this. Think of plum pudding more as like a blueberry muffin, okay, because they're British and they do things wrong. And so their pudding isn't good like ours. So anybody in Callum's section? Yeah, he's British too, but he's fine, I guess. Okay, so imagine I've got this sphere of mush, and there's little electrons in it, okay, but he knew that the whole atom was neutral, right? So if the electrons were negatively charged and they were in this mush, what is the mush? Positively charged. So that's his plum pudding model. Make sense? Yeah.
Didn't
So Thomson discovered the mass-charge ratio. What did Millikan do? He discovered the mass and the charge. Well, I mean, he didn't need to because it was already discovered. Does that make sense? Yeah, so we would attribute the discovery of the mass or the charge of electrons to Millikan. Yeah. Okay, so what did Millikan do? Oil drop. Okay, what was cool about Millikan? Who was his PhD student? Harvey Fletcher, who just had a building get knocked over just that way. But because we knocked down his building, we named the restaurant in the new engineering building after him. So it's called Harvey's. Really, I guess Harvey Fletcher did most of the work in the oil drop experiment, but Millikan was on payroll. So oil drop experiment, which discovered the mass and the charge of the electron. Straightforward enough? Okay, and then what did Curie do? Yeah, she did radiation or radioactivity. She also won like 2 Nobel Prizes, which is pretty sick. And then, what was that? I don't think you need to really worry about that. Somebody said it and it's true, so I wrote it. Okay. All right. And then what did Rutherford do? Gold foil. So what did he discover? The nucleus. Okay. And so that led us away from the plum pudding model into what model? Yeah, we call it the nuclear model or the Bohr model, I think. So basically what that says is, so he really what he discovered was most of the mass of the atom is in the middle, and it's positively charged. How did he know it was positively charged? He was shooting it with beta particles, which are positively charged, and they were like bouncing back at him. Okay, so he realized most of it's empty space, and the middle is a really dense positive charge, and so that led to the Jimmy Neutron model. Okay, where I've got a nucleus, and I've got electrons like flying around it, right? But most of it's empty space. Cool. We good? We good. Okay. Do this real quick. How many protons, neutrons, and electrons? Anybody want to fight? That wasn't meant to sound intimidating. Do those look right to you? Okay? Yeah. Figure out the neutrons. Good question. The question is, why can't I figure out the neutrons for these guys, and why not? I don't know the mass. So like I know like the average mass, but not the actual mass of these ones. Does that make sense? I saw a hand up here. Nope. Okay. Okay, you've got dark hair. You. What's your last name? Oh, never mind. You look like a friend of mine. All right. Let's move on. Is that your married name or your? No. Okay. She's not married. Okay. And she turns really red. Sorry, Matthews. All right, let's do this instead of looking at Sister Matthews over there. Let's calculate the average atomic mass. Okay, and you know the cool thing about this part? It's multiple choice, so who cares about significant figures? Okay. Somebody's like crying in the third row right now because... All right, you guys doing this? Okay, you should be. Yeah? Okay. Questions about how to do this? No questions? All right, how else could I have asked this question? What's another way I can ask you a natural abundance question? Right out in the back. Sorry. Go ahead. Awesome. So a different way I could ask this question is that I could give you this number and not give you one, all right, and not give you like two of these. Right? If I didn't give you one of those, would that be a very good question? No, because these all need to add up to 100. So that would be an addition or a subtraction problem, right? But if I didn't give you two of these, how would you solve the problem? I know that I just did different twos. Let's say I didn't give you this one, I didn't give you this one, but I did give you that. Okay, what would I have to do? I'd have to say, all right, this is x. And then this one is what? 1 minus 0.68075 minus x. Because that part still needs... So, does that make sense? Okay. We're not going to give you one that hard, but we would give you one maybe that has 2. Right? And so one of them is x, and the other one is 1 minus x. And you just have to do some nice, distribution of multiplication. But we're not going to worry about that right now because don't worry, be happy. All right. So we good? All right. Let's move on to light. Wow, are we really moving that fast? Nope. No, never mind. All right, do these. Do you guys want the equation sheet? This is when you all say, wow, Jeremy, you're so prepared. Thanks, guys. Can you even read it? If you can't read it, look it up. Is this working with me just kind of writing it slowly as you guys work on it? Yeah. Okay. Not that you're working slowly. Does that look right? What? Yeah, cool. All right, so let's talk a minute about the units here. So for these, you guys are really good at like getting quiet, unlike last time. I was surprised when I saw Shuyu here with all of his friends because they were loud last time and now everybody's quiet. So good job. All right, so when I'm using these equations, what is the unit of the speed of light? Meters per second, which is why wavelength is in meters and frequency is in 1/seconds. Does that make sense? So those are the units you've got to use. So this is my frequency. I should get 1/seconds, which is the same as hertz, which is the same as seconds to the -1. But I'm not going to write all of them because it's not hertz, 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 right? It's just one of them. Okay, haha. All right. Wavelength is then in meters, and then energy is in joules. All right. Go ahead and describe the Bohr model of the atom. Yeah, what's up?
Do we ever have to worry about electron volts?
Oh, I hope not, but if you do, they're right here. Yeah, but we've never used, there was like one smart work question, right? So I won't worry about it. Okay, what does the Bohr model of the atom look like? We kind of talked about it earlier. Awesome. So somebody said exponential what? Something. Yeah. That's good enough for me to know that you know what you're talking about. So the Bohr model says I've got this positive nucleus that has all the protons and the neutrons, right? And then I have these levels, these n levels. What happens to the n levels as I get further away? They get closer together. Okay, that's an important thing to understand. If you've done the practice test, you've seen the question that says something like, what's the biggest change in energy, right? And it gives you a bunch of different jumps. Some of them will look like they're the same unless you realize that the levels get closer and closer together. So, how far out do the levels go? Yeah, in theory, they go out as far as they want to go out. But why do electrons not go out to super far away levels? At that point, they probably just get grabbed by a different atom. Okay, so we only observe levels that like huge, like in the hundreds, like in space, where there's not other atoms for it to grab onto. Does that make sense? Yeah.
On the first exam, there was a question that asked, what is the most important limitation of the Bohr model?
What is the most important? I hope it didn't list 5 real limitations. Did it kind of? Who knows the answer? Does anybody know what that answer was? Yeah. Oh, yeah. Oh, yeah. Yes. That's the most important one. So that didn't light up my TA brain, but yeah, that's definitely true. So, and I wouldn't say it just works for hydrogen. What does it just work for? Things with 1 electron. We only use it for hydrogen, but technically you could use it for helium plus or lithium 2 plus, but we only use it for hydrogen. So, thank you. All right. So, is this what atoms really look like? No, but we still use it and we still do math with it. Why? It still gives us real information. Okay, for hydrogen, we can calculate like the wavelengths that are emitted from hydrogen, right? Those are real wavelengths that are really emitted from hydrogen. So it's not useless just because it's not 100% right? It's like other religions, right? They're not useless just because they don't have all the truth, right? Because they have a lot of truth, and so we love them. Okay, the world would be a lot of a worse place if no other religions existed but the true one, right? At least right now. But when Jesus comes, it's going to be great. So, all right. That's going on YouTube. Okay, calculate the frequency. You guys are probably, can you read that? Is that too small? Too small back there? Yeah? Okay. If you want someone to blame, you can blame the person who said yes, but you don't know who it was. So, oh my goodness. There we go. Okay. So calculate the frequency of the photon associated with an electron transition from n equals 2 to n equals 5. Is it absorbed or emitted? Let's answer the second question first. Is it absorbed or is it emitted? It's absorbed. How do we know that? Because it's going from 2 to 5. You have to push it away from the nucleus, right? But it wants to be attracted to the nucleus, so you've got to put energy in to push it away from the nucleus. Does that make sense? Okay, so can you guys think in your mind right now what the equation that you're supposed to use looks like? Can you picture it on the equation sheet? It's on the top right, right? I think it is. No? Is it bottom middle now because they changed the equation sheet? Anyway, but this is what it is. Oh, and what? You don't have to guess. Not by me. Are you chewing gum? That's why I don't chew gum, because it gets gross after like 20 seconds. Tic Tacs, bros. Then you eat mints, or you chew gum for 20 seconds near a trash can and spit it out. Thanks. Yeah. Shh. I'll talk to that. Is anybody here yet? Or do you want a little bit more time? Okay, take your time. So what is wrong? What is wrong with what I've done? Is it wrong that I did 5 first and then 2? Not necessarily. It depends on what they're asking for. But should I circle this as my answer? No, for 2 reasons. What's reason number 1? Yeah, they're asking for frequency. But if they were asking for wavelength, should I circle that as my answer? No. Why? It's negative, okay? Wavelength can't be negative, and so I would not, because I have 5 first and then 2, it gave me a negative number, okay? But it's the same number as if I did 2 first and then 5. So I guess what I'm trying to say is, don't worry about which, unless you like have a system and you already know, you don't have to worry about which one goes first. Just put them in, and you should be able to think about what your answer should be. Does that make sense? When could you have a negative answer? What would you be calculating if you got a negative answer? Yeah. Yeah, well, the change in energy of the electron when it goes down. That would be negative. Does that make sense? What about the energy of the photon when an electron goes down? Will that be negative? No, because a photon can't have negative energy. Okay, so it all depends on what the question is asking. So in this case, it's asking for frequency anyway, but I know the wavelength can't be negative, so I'll just make it positive and then change the frequency. And that gives me 6.9. Yeah? How are we feeling? Feels good? Okay, we're going to keep going. All right. Actually, I'll just leave that in case you want to see it. But let's do this. This is on the study guide, unfortunately. But let's just talk about it real quick. So I'd ask you to talk to the people next to you, but I'm guessing that a lot of you don't remember what this is. Maybe you do, and I'm just wrong, but that's fine. So what is a blackbody? Raise of hands. Raise of hand. Yeah.
Blackbody, like an opaque object at room temperature that as you add energy to it produces or emits radiation.
Oh, that was perfect. Okay, so at room temperature, it's just normally it absorbs all light. It doesn't reflect anything. It's opaque, so they usually appear black, like the coils on your stove. But what happens when you put energy into a blackbody? Yeah, so eventually it has so much energy in it, it just can't hold the energy anymore. And so it releases that heat. Now, or it releases that energy as electromagnetic radiation. So why do we say it heats up? Because that's how we observe it, right? Like we feel it getting hot. But then it's not just that it releases heat, right? Heat is just infrared radiation. It's just on the electromagnetic spectrum, right? Okay, because not only does it release heat, what else does it release? Light. Eventually it starts emitting from ultraviolet, and then it starts emitting into the, sorry, not ultraviolet, infrared, and then the more energy you put into it, the higher energy radiation it gives off, which is why then we see it get red hot, and eventually it gets white hot. What does it not get? It does not get ultraviolet hot. Okay, so classical physics said that if I keep putting energy into this black body, it should keep emitting at higher and higher and higher frequencies, but it doesn't. It stops at ultraviolet. What do we call that? Ultraviolet catastrophe. How did they solve it? Who solved it? Planck. CK? CK. And what did he do to make it work? He said, let's assume that energy is quantized, that it's only available in little packets, that it's not actually continuous, and you don't need to worry about it. But when he did that, all of a sudden his model predicted what actually happened, which was evidence that energy is in fact quantized. If you watch Ant-Man and the Wasp, there's one point where they go to like the black professor's lecture. I don't know if you know what I'm talking about. And on the board behind him is this graph. You guys know that graph? About the ultraviolet catastrophe, in case you're wondering. Now, as you're watching that movie, tomorrow night, you can impress your date. All right. We good? Okay, we're good. Okay, calculate the kinetic energy of an electron emitted from silver metal when hit by a photon with that wavelength. That's the work function of silver. Oh, do you want the equation sheet? Oh, we're good. It's there. It's a nice face, Lauren. That's what it looked like. All right, so what are we talking about here? You guys remember work function? Do you know what it is? So work function work function has to do with the photoelectric effect. So what's the photoelectric effect? It says that when I take this laser pointer and I shine it at a piece of metal, if it stays on, then if this laser pointer has enough energy, it can kick electrons off of that metal. Okay, in this case, it's probably not going to kick them off because they have nowhere to go, but maybe it will. I don't know. Does that make sense? So my photons are coming in like or like boxing gloves, and if they have enough energy, they can punch the electrons out of the metal. That's the photoelectric effect. Okay. Well, work function is that minimum amount of energy required to get the electron to kick off. Okay, so our photons, they have a wavelength, they have frequency, they have energy, right? And if they have enough energy, they can kick off an electron. The work function is that enough energy. So what we say is that h nu, what does h nu represent? That's the energy of what? of my photon from my green laser shining in, okay? Shh. That energy goes in, and some of it is used to remove an electron, just to rip the electron out of the atoms. Does that make sense? That's the minimum energy required. But what if my photon has more energy than that? Okay. It kicks the electron off with more kinetic energy. Does it kick off more electrons? No, just like when I swing my leg at a soccer ball, if I swing harder, I don't kick more soccer balls, right? I only ever kick one, but if I kick it harder, I just give it more kinetic energy. Okay, so that's what's happening here. So this is the equation we've got. It's the same equation that's right here, but they've rearranged it in a way that I don't like. So I'm going to do this one, okay? All right, so what do I need to know in order to find the kinetic energy? I need to know the energy of my photon, and I need to know the work function. Well, I know the wavelength, so I'm just going to replace that frequency with wavelength. And that's going to equal my work function plus kinetic energy. I'm going to drag this back over again. Go away. All right, so hc over 45 times 10 to the negative 9. Okay, and when I do that math, I got a kinetic energy of 3.6 times 10 to the negative 18. Anybody else get that? Okay. Any questions about how I set that up? Feel good? All right, we feel apathetic. Sweet. So now do this one. Yes. You guys see the mass of an electron's right here? All right, how do we do? So, oh, yes. Let's do 1, 2. Go ahead. Yeah, you. Shh. How did you find kinetic energy? Okay, and then you did... Sorry, that was a stupid question. Of course, that's how you found kinetic energy. And then what did you do? You set it equal to... Gotcha. But where's your frequency? Because you have the wavelength. Okay, I see. You just set them equal to each other. And you got pretty much the same answer? So that's kind of how it's derived, but it's not really. I don't know if that'll get you the right answer. I'd have to look at it. All right, but what's different between these wavelengths and the other wavelengths we've done? The other wavelengths were for what? Photons. Okay, photons are little packets of energy. They don't have mass. Okay, if we want to figure out the wavelength of something with mass, what are we going to use? The de Broglie wavelength, which is for something with mass, which is why there's mass. And what's this V? Velocity. Okay, and so you plug it in just like that, and you get the answer. Questions? Did you have a question, Joanna?
Yeah, so like frequency only changes the rate of electron coming off, right?
So I think you're probably referring to this one.
Yeah, and so like there is something that makes
Okay, yeah, I know what you're asking, I think. Okay, so this is a question about the photoelectric effect. So let's say that I take this guy and I shine it on metal and it's kicking off some electrons, and I increase the frequency of the light. So instead of green, I'm using violet. Okay, what changes? Yeah, the kinetic energy changes, because if I switch from a green laser to a purple laser, all I've done is upped the energy of my laser, right? So it's going to kick off electrons faster. Okay, what would I change if I wanted to kick off more electrons? I would increase the intensity, which refers to the number of photons. And how do we observe intensity as human beings? Brightness. So I could have this green laser and another green laser that's the exact same color but brighter. Okay, that would be kicking off more electrons. Does that answer your question? Yeah. Cool. Okay. All right, modern atomic theory. You guys remember these guys? Okay, take a minute, try and answer both of these with the people around you. All right, let's talk. So what is psi? So psi is called a wave function. It's a solution to what equation? Yeah, Schrödinger. That's not how you spell it. I don't know how to spell it. Equation. Okay. Which you don't need to know, but maybe that's a good thing to know. Like, you don't need to know his equation, but... And what does it tell you? It tells you, well, it tells you the wave functions. It tells you the allowed energy states. Of the electrons. So you feed in, like, your quantum number. This is, like, super simplified, guys. Go take Chem 460 something if you want to figure it out. But you feed in your different quantum numbers, and it kicks out the wave function which says, this is, with those quantum numbers, this is what your electron behavior is. This is what your electrons are doing, if that makes sense. Okay? But we don't, in Chem 105 especially, we don't care about psi. What do we care about? Psi squared. Okay? And that is, if you square it, what do you get? Yeah, you get the probability distribution. I don't remember if you remember this graph. It had like a bunch of dots on it. You guys remember that graph? Okay. It gives you a probability plot of where the electron is likely to be. Okay, so why is that useful? So then we say, let's encompass 90% of that and call it a what? We call it an orbital. So that's how we get our orbitals. They're just solutions to a mathematical equation. Okay? And what is an orbital? Yeah, it's a volume where an electron is likely to be found. How often? 90% of the time. That's an important number to know, I think. Okay, cool. So then, speaking of quantum numbers, how many electrons are in the n equals 4, L equals 2 subshell? Anybody remember? Who's like, let's talk about it. Okay, I know that some of you know the answer. How many of you really want to like dive into this? Okay, that's okay. There's nothing wrong with that. I just don't want to do it if everybody's like, we know this. Okay, this won't take very long. All right, so we have 4 quantum numbers. What are they? N, L, M sub L, M sub S. N, what do you call N if you're a nerd? The principal quantum number. What do you call it if you actually care about what it is? You say N. So we usually refer to it as energy level. Or shell is another one. Okay, they're just like the N's that we were dealing with the hydrogen atom. It's the same N's. So what could N be? 1, 2, 3, 4, yeah. Cool, so those are the energy levels. Okay, within those energy levels, though, we have the L quantum number, which tells us what? What's the nerdy name? Angular momentum quantum number. I'm saying that because maybe it'll pop up. I hope it doesn't. But, and then what is a better name for that? We call them subshells. We could also just call them shapes. Okay, and so what are possible values for L? 0 up to n minus 1. What do we mean by that? Well, what we mean by that is at different n levels, you're going to have different shapes of orbitals. Okay? So if n equals 1, L can be 0 up to 1 minus 1, which is 0. So L can just be 0 when n equals 1. That means that at n equals 1, there's only one shape of orbital, right? And what is it? S, because a 0 represents an S. Because L represents what? Number of, do you remember that? Number of planar nodes. Okay, we'll talk more about that. Let's keep going. So if n equals 2, L could be 0, but it can go up to 2 minus 1. So you go up to 1. Does that make sense? If n equals 3, I could have 0, 1, or 2. If n equals 4, I could have 0, 1, 2, or 3. Okay? We already said that if L is 0, that's an s orbital. But what if I take an s orbital and I stick a planar node on it? What does it look like? Looks like that. Okay, that was really bad. Okay, that's an s orbital with a node on it. So if I have one planar node, what is that? That's p. What if I put a node through that? What do I get? If I have 2 planar nodes, I get a d. And if I have another planar node, I get an f. You guys following? Okay. So that's what L is. So now I know that in n equals 3, there's 3 s orbitals. Those exist. 3 p orbitals exist. 3 d orbitals exist. Okay? But how many of each of those orbitals are there? That's what m sub L tells us. Okay, so I could call m sub L the orientation or just the orbital. In other words, if I want to know a specific orbital, I need to know n, L, and m sub L. Okay, and what are the possible values for m sub L? Negative L up to positive L. So if L is 0, m sub L is 0. Okay, what does this tell us? How many 1s orbitals are there? 1, because there's only one number there. Okay, so that's a 0, negative 1, 0, 1. Sweet. So, how many orbitals are there when n equals 4 and L equals 2? There are 5 orbitals. N equals 4, L equals 2. There are 5 orientations of that 4D orbital. Okay? But that's not what the question asked. The question asked about electrons. Well, what does m sub s tell us? It's the spin. It tells us about a particular electron. What are the values for it? Minus 1/2, plus 1/2. All that means is that each orbital can have 2 distinct electrons in it. So, we just said that in n equals 4 and L equals 2, there are 5 orbitals. So how many electrons? 10 electrons. Because each orbital can have 2 electrons. We cool? How many of you might draw that on your note card? Maybe? Maybe not. Okay, never mind. Let's keep going. Sweet, let's do some electron configurations. Okay. Boron. Ready? We're going to all chant it like a cult. Okay. Ready, set, go. 1s2, 2s2, 2p1. We're only going to boron. Yeah? Okay. Those of you who said 6, repent. Okay. Now let's do, oh, we're good. Okay. Now let's do copper. You want to start at the beginning? Yep, let's do it. Okay, ready, go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Oh, Jeremy got us. Okay. So, okay, do you guys remember why it does that? So if I were to draw this out, that's what it would look like based on what all of you guys said, which was wrong. Not all of you, some of you, but that's okay. Why is it 4s1, 3d10? Who wants to answer? Yeah. Awesome. So the energy states that are nice and low energy are totally full, half full, or empty. Okay? And so it takes a little bit of an investment of energy to take that guy and put it there. But once it does it, it gets to relax. Does that make sense? It's lower energy to have it there. So it's worth it to put in a little energy to lift it up because it gets it to a lower energy state. Okay? So what atoms do this? Well, copper's column does it. Chromium's column also does it. So chromium's will turn out like a 4s1 3d5 because it's going to want to get half full. Does that make sense? And I know that like tungsten doesn't, you don't need to worry about that. We're not going to give you tungsten. That would be dirty. Yeah.
Would it still do it even if it's charged?
So that's a good question. So let's talk about that. So let's say that I asked for the electron configuration of copper plus. What's the best way to get the right answer? The best way to get the right answer is to draw out the electron configuration for copper and then take away an electron. So if I'm a transition metal, where do I lose my electrons from first? The S. Okay, so in copper's case, if I was doing copper plus, I'd draw this out like this, and then I would erase this one. Okay, I don't know if that answers your question. That you remove it, or? Yeah, you're always going to remove the highest one first. But 4s, the way I've drawn it, 4s is lower. But once they get filled up, it's actually higher. You just need to remember, take it out of the if it's a transition metal, take it out of the s orbital first. But all right, keep going. Other questions about this? Okay. Okay, periodic trends. Take a minute and let's describe these together. Ready, go. All right, let's bring it back. Okay, so there's two things that we can use to describe all of these trends. Okay? The two things are Z effective and N level. Okay? The reason it's Z effective and N level is because the force of attraction between my electrons on my outside and my nucleus on my inside is governed by what law? Coulomb's law, because everything in this class is governed by Coulomb's law. Okay, but I could replace these variables because you're never going to do math with this, right? So the force of attraction is based off the two charges and this distance between them. Okay, well, what are the two charges in my atom? I've got my nucleus and I've got my electrons, right? So I could replace this with Z, which is the total charge in the nucleus, and the charge of my electron. Yeah? Okay, but let's say I have a really big atom. Do my electrons on the outside feel everything from the inside? No, because of what we call electron shielding. And so, instead of Z, we use this Z effective term, which just means how much positive pole is felt at the outside of the atom. Okay? So instead of two charges, I'm going to put Z effective in my charge my electron. And then what about this distance? What could we replace that with? N level, because as my N level increases, we know our electrons are getting further and further away. Does that make sense? Yeah. This is not something that you learned that you have to know. This is just me explaining these trends. Sound good? Okay. Some of you are like, oh, okay. So there's two ways that I can increase the force of attraction, right? What are they? I could increase the Z effective, or I could decrease the N level, right? Well, which direction does Z effective increase on the periodic table? To the right. If I go like that, my Z effective goes up. Which way does N increase? Going down. So which corner of the periodic table will have the strongest hold on the outside electrons? This corner. Because that's where my Z effective is high and my N is low. You guys see that? Yeah. So if I know that this corner has the highest pull on my electrons, we can explain all of this. Okay? So atomic radius. Well, we already talked about N increases going down, right? So where's going to be the biggest atomic radius? Down here. Does that make sense? Just have the most N levels. Plus, As I go across the periodic table, my Z effective is increasing, which is pulling the electrons closer. You guys see that? So radius increases down and to the left. Ionization energy. What's ionization energy? The energy required to rip an electron away, right? And so where is it going to take the most energy to rip an electron away? Top right, because those have the strongest pull on the electrons. Okay, electron affinity. Oh, go ahead. One more time? Yeah, so the question is, aren't work function and ionization energy related? They are. Work function is just more narrow in its scope because it just refers to metals.
Oh, really?
Yeah, work function is just for metals. Photoelectric effect is just for metals. Yeah. Okay, so electron affinity, what is that? How much it wants an electron, okay? So if up here has the strongest pull, what wants an electron the most? Up there. What about electronegativity? What is electronegativity? It's very, go ahead. But that's electron affinity. Is that what I asked for? No, that's electron affinity. How do we amend that for electronegativity? So he's right, except let's add a few more words. It's how much an atom pulls on electrons in a bond. That's the difference between an electron affinity and electronegativity. Electronegativity is in a bond. But it's the same idea, so we're still going to do that. Sound good? All right. We're fine. All right, let's do some of these. I want you to draw it. Draw the non-bonding electrons, non-zero formal charges, bond polarities, electron geometry, molecular shape, bond order, orbital hybridization. Because I'm going to have to ask all these questions anyway, we may as well do them all at once, right? So, this is what I'm going to do. You guys start working on it in about 60 seconds. I'm just going to start working on it slowly. Sound good? Okay, go ahead. What? He was looking at me. Huh? Oh. What? Sure. Because you can't figure out the geometry of the whole thing. All right, how we doing? You guys want a couple minutes more? You're almost done copying all my stuff. Awesome. That's learning in its finest. All right, what questions you guys have about these things? Yeah. What's the what? So the question is, aren't there some cases where there's only one electron? Yeah, if you ran out of electrons and you had one left. But I don't, it'd be some weird ion probably, and I'm not sure. Actually, I bet if you just had NO2 instead of NO2 minus, then you'll be missing an electron. You'll probably have one by itself, which is fine, but don't resort to that. Make sure that you're doing everything right before you, it's multiple choice, so. Yeah. Yeah. Good question. How do you calculate bond order? So if you see here, if you look here, I labeled the bond orders like there's two different bond orders here, right? That's because there's two different types of bonds. Okay? So bond orders have to be the same type of bond. So I've got a CH bond, and both CH bonds are single bonds. That's a bond order of 1. Does that make sense? Okay, when it gets funky is if you got resonance. So this guy, that's a double bond, and that's a single bond. What's the average between 1 and 2? A half, right? 3 3 halves because this double bond is being shared. So I can think, oh, I have a double bond and a single bond, so when the double bond gets shared, I'm going to have 1.5. You can also think of it as I've got 3 lines over 2 spots. So 3 halves. Does that help? Yeah. Sweet. Yeah. Shh. Hey, good question. Why didn't I include that? So the question is, how do you know if the molecule is polar? It just means it's not balanced. So its shape is not balanced or symmetrical. Okay? So is this CH2Cl2, is that balanced? What if I drew it like this? Is that balanced? Okay, it's not, because if it was actually a plus sign, it would be balanced, right? But it's not actually a plus sign, it's tetrahedral. And so your Cl's and your H's don't balance each other out. Okay? Which one of these is going to be nonpolar? This one. Why is that nonpolar? Well, it's square planar. So this one really is a plus sign. Does that make sense? So that one is going to be nonpolar. Okay. Yeah. So that's fine. That's not wrong. But it's not actually, if it was flat in 2D, that's true, but it's tetrahedral, so that's not true. Yeah. That's because it's tetrahedral, that's why you could draw it both ways, because you're just kind of turning the molecule. Yeah. Correct, as long as the molecules on the sides are the same, but yeah. Yep. Okay, and anything with no lone pairs is also going to be balanced. Okay. All right. Label all orbitals and complete the molecular orbitals for CO. Oh, I already labeled them, so now you don't have to. Okay, so just let's do this for CO and tell me paramagnetic or diamagnetic and what's the bond order. Do you mean label them? Hopefully not, but you'll see a question on the practice test where it's not labeled. You got to be able to answer it still. What's up in the back? Yes. Okay, I'm going to scroll up real quick and answer this question about the Lewis structures. So the hybridization for xenon tetrafluoride. How do I figure out hybridization? Steric number. So what's the steric number around this xenon? 6, because I've got 4 bonds and 2 lone pairs, so that makes 6, right? Which means I need to hybridize 6 orbitals. So I have an S, and then I have 3 P's, and then I have 2 D's. So sp3d2. Okay, what's this sp3 out there? That's for the fluorine. The fluorine's also hybridizing. It's got 3 lone pairs in a bond, so it's sp3. Okay, keep going. How do we do? How did I know how many electrons to put in? Yep, I just say I know carbon's got 4, oxygen's got 6, so I've got 10. It's that easy. Just fill it up from the bottom. Good? Yeah.
I remember there being a lot of questions about like which theory is best for what kind of thing.
Yeah, let's talk about it. Good question. Okay, so what are the 2 theories we've got? Valence bond and molecular orbital. So valence bond says, so these are just bonding theories. In other words, yeah, we'll talk about it. So these are bonding theories. Excuse me. In other words, these are not two people's, but two theories of, all right, I know that atoms bond to each other. What does that even mean? That's what these two things are trying to explain. Why do we use both of them? Because both of them are partly good, right? No more religion analogies. Okay, yeah. You really want me to include Vesper?
Well, there was a question. It was a question.
Yeah, but it's just like under here.
Well, we don't understand that he's like.
I'm not done talking about it. Holy cow! If at the end of the discussion you're still not satisfied, I'll add a column, but I'm going to talk about Vesper. Okay. So, valence bond theory at a fundamental level says if I've got a carbon and I've got an oxygen and they're bonding, what does that mean? That means carbon's orbitals are overlapping oxygens. Does that make sense? Orbitals are overlapping. That's what valence bond theory says is the definition of a bond. Okay? So like when we talk about hybridization, that's valence bond theory because xenon's orbitals are xenon's orbitals. Fluorines are fluorines and they just overlap. Okay? So what is valence bond? Based on the fact that valence bond has Lewis structures, what is that good at telling us? Shape. And what really tells us the shape? That's what tells us the shape. Because it tells us electron groups are going to repel each other. That's why we get things like tetrahedral. Does that make sense? So it tells us shape. What else does it tell us? Right? We could figure out polarity based on these drawings. Anything else that it's good at? What was that?
Bond angles?
Yes, bond angles. What about molecular orbital theory? Okay, fundamentally molecular orbital theory says when carbon with its atomic orbitals and oxygen with its atomic orbitals come and make a CO bond, what happened to the atomic orbitals? They disappear. They no longer exist. Okay? They blend together, and what do I get? Molecular orbitals with funky names like these. Okay? So these are just new orbitals that didn't exist before the bond happened and now exist now that the bond happened. And what is molecular orbital theory good at showing? So I don't know about you, I don't get a lot of shape out of this, but you're right that you can, well, I mean, that's what this is. This is molecular shape. But technically the answer is yes. But you don't know how to get shape from it, if that makes sense. Okay? Okay? Yeah? Yeah, so just like hydrogen can absorb and emit stuff, I don't know if I spelled emission right, molecules can absorb and emit stuff. And we now understand that because of the energy levels. Okay, and the last thing that we talk about, bond order. We also got bond order from that, right? But which one is more accurate more often? This one. Okay. Did that satisfy all of the Vesper wants over here in the corner? Yeah? Everybody satisfied? Okay, he's like so done with me. Okay. Nomenclature. Go ahead and name these. Or do you just want to name them together? We'll name them together. Okay, what's up? So yes, except I want to keep moving. So I would just refer you to the PowerPoint slides. Okay. So what's the first question I've got to ask when I want to figure out what a name is? Yeah, is it ionic or covalent? Okay. Or what else could it be? I mean, it couldn't be anything else, but what other sets of naming rules do we have? Acid. Okay. So what is this? The real answer I was looking for was covalent, but that's okay. That's dinitrogen pentoxide. What is this one? Which category does that fall into? Acid. What type of acid? Oxoacid. So this thing is So PO3 3 minus is Phyte, which means the acid would be called phosphorus. Right? 8 turns to ik, ite turns to us. Ringing some bells. Okay, what is this? What does it fall under? Okay, I'll just write it. That's an acid, but it's a binary acid, so we have the hydro thing. And then this is ionic, so what do we call it? Sweet. This is my reminder to you that if you can't name stuff, you should figure it out. Okay. Organic chemistry. So are these isomers? Oh, I got some yeses and some nos. Who wants to fight? Okay, how do we figure this out? Well, it would help to know what an isomer is. So what's an isomer? Yeah. Perfect. Same formula, different molecule. Okay? Same formula, different molecule. Now there's multiple ways to get different molecules. Therefore, there are multiple types of isomers. Okay? But an isomer just means it's the same formula, different molecule. So are these the same formula, different molecule? Yeah. They are. If you were to count all the hydrogens, you get the same thing, carbon, same thing. So yes. Okay, and what type of isomers are these? Structural, which is the same as constitutional. Okay, what does that mean? That means that my atoms are connected different. My Lewis structures look different. That's what that means. And those are obviously connected different. Differently, right? Because it's an adverb. Okay. All right, so now let's find all the chiral centers. So what types of isomers have chiral centers? Okay. So if I had, never mind. Are enantiomers connected differently? No, because then they'd be structural. Okay. They're isomers because they have chiral centers, and when you take the mirror image of the chiral center, you get a different molecule. Same formula, different molecule. But in this case, it's not because it's connected different, it's because it's just arranged different around the chiral center. So let's find them. What do you need to have a chiral center? 4 different connections. So let's start here. Chiral center? No. Why is it so easy to throw that out? There's a double bond, so it can't be connected to 4 things. Does that make sense? Okay, what about, so yeah, no. What about this one? Oh, let's go. What do you got? Okay, Bryce says yes. And he says yes too. Okay, so what are my 4 groups? I've got this thing, which is like a CH3 group. I've got a hydrogen. And then I've got the ring going this way and the ring going that way. And those 2 rings look very different. It's not tricky. It's just how it is. But that's okay. Okay, what about this guy? Questions? Oh. Okay, we good? This is your reminder to go back and figure those out if you haven't. Okay, so what's our, yeah?
So for organic chemistry, the learning objectives, it says functional groups.
Yeah, good question. So on the learning objectives, it talks about functional groups and knowing them. You don't need to know them. Okay, that was from last semester. They forgot to take it off when they made this class easier for you guys. So Okay, there's one type of isomer we haven't talked about. What is it? Yeah, geometric, which is cis-trans. What do you need to have a cis-trans isomer? Double bond. Are these connected differently? No. The things connected to that carbon are exactly the same as the things connected to that carbon. Do you agree? Okay. Because if they were connected differently, they'd be structural. So these are not connected differently. They're arranged differently, though, because of the double bond. Okay. All right, gas laws. Let's talk about the assumptions of ideal gases. So usually at this point, people are like, Jeremy, just talk. So I'm going to just go through these, but there's problems too, don't worry. So assumptions of ideal gas, there's 5 of them. Okay, we've got no intermolecular forces. We've got elastic collisions, tiny molecular volume, and kinetic energy is proportional to temperature. Okay, so which of these have we talked about the most? Intermolecular forces. So if you remember the question that's like, which of these is least likely to be an ideal gas? It was on a practice test. Okay, and it was like London dispersion, London dispersion, London dispersion, London dispersion, hydrogen bonding. Okay, do you guys, some of you maybe remember that. Something that has hydrogen bonding is less likely to act ideally compared to something that is London dispersion because its intermolecular forces are stronger. So this assumption number 1 breaks down. Yeah? Okay. All right, ideal gas problem. What temperature would be required for a hot air balloon that is normally that many liters at that temperature and that pressure at ground level to expand to that many liters at that pressure? Did anybody else get that? Okay, bad problem. I ate it up while sitting on the couch watching Gilmore Girls 4 hours ago, so. It's a good show. I mean, it's just sort of like gets you in the feels, you know? Okay. Questions about that, though? So what do I think when I read this problem? I think I've got a gas in one situation and I'm changing the conditions. Okay, but because we're in Chem 105, we just assume it's ideal. And so my PV over NT is always going to equal R. Always. So in conditions 1, PV over NT is going to equal R, and in condition 2, PV over NT is going to equal R. So they're going to equal each other. And then I can get rid of moles. Why? So I'm assuming that no moles are being added, which is a bad assumption because it's a hot air balloon, but whatever. And then I just plug everything in. Okay. So obviously we're not going to finish this by 8, but because I'm making the video, I'm going to finish the whole thing. You're welcome to get up and leave, just so you know, but I'm just going to keep working. Sound good? And if you need to leave because you're just sick of it, you can watch the video later. Okay. So how many liters of NH3? Oh, but I guarantee 5% higher on the test if you stick around. Just kidding. Actually, if you look at the grade distribution per day, the average grade goes down the longer the test is open. So statistically, that means if you take it on Saturday, you will do better, right? That's what that means? Oh. Correlation, causation, right? Okay. How many liters of ammonium at 850 degrees Celsius and 5 atmosphere are required to react with that many grams of oxygen in that equation? That was in the denial phase, almost to the acceptance phase. So what do you think? Where am I going to start? Yeah. Perfect. So that was awesome. Okay. So I'm trying to react with 32 grams of oxygen. Could I figure out how many moles of ammonium I need to react with 32 grams of oxygen? Yeah, you could do that. And if you know the amount of moles of ammonium that you need, and you know the pressure and the temperature, could you find the volume of ammonium that you need? Yeah. So I would go. Oh, thank you. So if I want to react 32 grams of O2, that's how much ammonium I need. And I know that PV equals nRT. I'm looking for my volume. nRT. I got 14.7. Anybody else? Confirmation? Awesome. So here's 2 ways that we can ask you to use the ideal gas law. We can ask you to compare a gas in 2 different situations, or we can just ask you to use properties like pressure, volume, temperature, and moles to use 3 of those to find the 4th. In this case, it was in the context of a reaction, but all we're doing is using 3 of those to find the 4th. All right, what's the density in grams per liter of sulfur hexafluoride at that temperature and that pressure? When you see density of a gas, you should think, thank goodness that I can get points for this problem. Okay? Because that's wrong. Because they gave you the equation of a density of a gas. Okay? And they added that this semester. So like class is even easier. All right, density is PM over RT. Pressure to, what's M? It's the molar mass of sulfur hexafluoride. Molar mass of sulfur hexafluoride. 7.12? Sweet. I know I'm going quickly, but that's okay. So are the units correct? Do you want me to prove it? Okay. My pressures in atmospheres, this 146 is in grams per mole. This 0.08206 is in liter atmospheres per mole K, and the temperature is in K. You guys kind of see what I did there? Yeah. Cancel, 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 grams per liter. Sweet. Okay. All right. Last thing about gases. You've got an unknown gas, it's pumped into a container. It's already got some O2. The unknown gas exerts that pressure. That's the total pressure. What's the mole fraction? Well, remember, mole fraction is going to be moles of O2 over total moles. And sometimes we use this chi to describe it. But the mole fraction and the pressure fraction are exactly the same. So moles of O2 over total moles is going to equal pressure of O2 over total pressure. Does that make sense? If 20% of the moles in here are oxygen, 20% of the pressure in here is oxygen. Oh, but it wants the unknown gas. Oh yeah, unknown gas, whatever. This is unknown. Feel okay? That's partial pressure. Okay. That's what I just did. So then, yeah, so if you knew the mole fraction is 0.205. If I knew the mole fraction was 0.205 and the total pressure was 11.2, then I would just multiply these together and I'd get the partial pressure. Yep. Okay. Intermolecular forces. There are 6 of them. Let's list them. What's the strongest? I always get people saying hydrogen bonding. It's not hydrogen bonding. That's why water is a liquid at room temperature and salt is a solid at room temperature, because ion-ion is stronger than hydrogen bonding. Those are the 6 of them. I would encourage you to go back and look at what some of the questions that we give you about intermolecular forces are. A lot of them, basically what you're going to have to do for these questions is figure out, all right, what's the intermolecular force in each of these compounds? Maybe that's just the answer, but often the question is about like boiling point or stuff like that. Okay, I don't want to go into all that right now, but yeah.
Quick question: if something has a hydrogen bond, isn't it automatically dipole?
Yeah. So if we ask for all of them, everything always has London dispersion, and hydrogen bonding is just a strong form of dipole-dipole, and so you would have all 3 of them. Okay. If you want to know more about intermolecular forces, on my YouTube channel, there's a series of videos called Intermolecular Forces, and you can watch them. It was back when I had a different screen recording thing, and so I could only record in 5-minute snippets. But it's just one playlist, so they just play one after the other. So anyway, okay. Stoichiometry. Oh, we're actually almost done. Okay. Do you guys want to work on these alone or just together? Okay. So, how much CO2 is produced in the combustion of 275 grams of heptane, 28 moles of O2? No, sorry. Again, that's just like on this. Yeah, I just accidentally left it. Okay. So, what tells me that I need a reaction equation? Okay. Somebody said stoichiometry. Yes. Okay. But what else? What about this question? So what tells me is that it asks for CO2, and it gives me information about heptane and O2. Those are different things. So I need some way to relate heptane and O2 to CO2. Following? And the only way I have to relate that is an equation, so this is a 16. Is this 11? All right, so now I have molar relationships between all these molecules. I want to figure out how much CO2 is made, but they give me amounts of both reactants. What does that mean? Limiting reactant. So this is how I'm going to figure out limiting reactant, but there's lots of ways to do it. But I'm going to just take both of my things, convert them to CO2, whichever one makes less is limiting, plus then I've already answered my question about how much CO2 is made. Okay? So wow. Molar mass of heptane. Anybody else get that? Yeah? I know that was fast, but confirmation? So I just took my reactants and converted them both into CO2. So which reactant is limiting? Oxygen, because it made less CO2. How much CO2 am I going to make then? This. Okay. What is this number? Theoretical and fake. Do I ever make 847 grams of CO2? No, that's just how much I could have made if I had this much heptane and unlimited oxygen, but I don't. So I'm only going to make 784. If it says excess oxygen, that means don't think about the oxygen. Just think about the one they give you. I don't know who asked you asked that. Okay. I was just generally looking in that direction. All right. If 700 grams of CO2 are formed, what's the percent yield? What is percent yield? What's my actual? Yeah, because it says I formed 700 grams. So that's my actual formed. Theoretically, how much could I have formed? 784. All right, now find molecular formula from percent compositions. How do we do this? Who wants to walk us through? Yes, go ahead. Okay, I'm going to pretend that I have 100 grams, which means I have 64.8 grams of carbon, 13.62 grams of hydrogen, and the rest. Oh, come on, Jeremy, why do you make it so hard? And 21 point, I can fit this all on here. of oxygen. I take those grams. A molecular formula, those numbers in the bottom, H2O, those represent what? That was a poorly asked question. Those ratios are molar ratios. It means that for 2 moles of hydrogen, I have 1 mole of oxygen. So in order to get those numbers, which is what I'm looking for, I know that my thing is CHO. I'm looking for these numbers. I need to get moles. Okay, so now I have my moles of each thing, but I don't just want moles. What do I want? I want mole ratios. Okay? So to get mole ratios, okay, what am I going to do? Divide by the smallest. Could I divide by the biggest? I could. It just would give me really tiny numbers, and I'd have to multiply a lot to get whole numbers. By dividing by the smallest, I divide by the smallest to guarantee that the smallest number I get is 1. So I don't get any little decimals. I get 1 there. What do I get here? 10. What do I get here? 4. Awesome. So it's C4H10O1. But is that the answer? No. Why? What is that? That's the empirical formula. How do I check to see if that's the molecular formula? Find the molar mass of this, which is 74. So is that the molecular formula? Nope. What do I have to do? I have to multiply it by 2 because to get this from this, I have to multiply by 2. Yeah. I see. Yeah.
Also, are you ever going to have something that has just 1 oxygen?
Yeah, you could. Like, yep. Okay. Sweet. Question about how to do that? Okay, what's the other problem that's associated with this stuff? Combustion analysis. Okay, remember that's a type of problem you should know how to solve. That's not combustion analysis. That's when we say you burn it and you get this much CO2 and this much water, and then ask you for the empirical formula. Okay. All right, let's do this real quick. You guys all just got shell-shocked by this stuff. So, oh, that's funny. I thought you said you were going to stay the whole time. Okay, that's fair. That's fair. Okay. How do we calculate work? That doesn't make sense. Of course she did. It's me and her. I mean, except it's compressing. Final. Hold on, what am I doing wrong? Oh, it should be positive. Yeah? Negative P delta V. Okay, we're feeling good because that's the end. 2 problems left. Okay. trying to find the delta H of this reaction. How do I do it? I'm given bond enthalpies, so what am I going to do? Broken minus formed. So I'm breaking my reactants. So I'm going to have a 1072 and 2 HOs. I'm forming my product, so I'm going to have 2 CO double bonds and a 436. Okay, what were the other, does this make sense? Okay, this is when you're given bond enthalpies, you do broken minus formed. There were 2 other ways that we calculated the delta H of a reaction. What were they? If we have, so usually we refer to it as Hess's law, if you're given like 2 or 3 reactions that you flip and multiply, right, to add up. And the other way is if we, instead of giving you bond enthalpies, we give you delta H as a formation, then what do? Products minus reactants. Okay. Find the heat required to freeze 500 grams of water that's 47 degrees. So we're starting as water that's 47 degrees, and we want to freeze it. So how many Qs are we going to have? 2. Oh, my bad. We want to freeze it. Okay, so we're going to have a Q that's going to cool it down. So what's that equation going to be? You guys make me so proud. And then we're going to have a Q. That wasn't sarcastic. It just came off that way. Okay. So I've got 500 grams. My specific heat for liquid is 4.184 joules per gram. That one says Kelvin. Doesn't matter. And my temperature change? Negative 47. That gives me, wow, negative 98324 joules. Okay, and then I've got to freeze it. What's that going to be? N delta H of fusion, but fusion is doing what? Melting. So I've got to use negative delta H of fusion. I've got 500 grams divided by 18 grams per mole. That gives me my moles. And delta H of fusion is that, so negative 6.01. Equals negative 166.9 kilojoules. Did I do something wrong? Oh, yeah. So then my Q is going to equal 98.324 kilojoules minus 166.9 kilojoules. Anybody want to fight? Okay, what's the equation for delta G? Yep, and y'all, a bunch of y'all got problem 2 wrong on test 4. Are you raising your hand because you got it wrong? Correct. Same with delta S and delta H. But in this equation, it doesn't matter that it's a different temperature. So, but yes, yeah. Okay. I said something I said I thought I should have stopped. So when we do products minus reactants, that's at standard state. But the way we use this equation, those are like they're at standard state. So you can do products minus reactants for those, but delta G, then you can pick the temperature. The values we give you always have knots, even if they don't draw them. Yeah. All right, guys, that's it. So get out of here. Good luck on the test.